Hey guys, this is Mrs. Lyons, and I thought I would take a couple of minutes and just go over this practice test with you so that you are as prepared as possible for our upcoming assessment. So the first thing I want to look at are these two pictures, okay? Because these two pictures tell us a lot, okay? Picture A has heat going from the system. Pen doesn't work. From the system to the surroundings. Okay, so heat is exiting the system. So that makes this picture a representation of an exothermic reaction, which means over here we have heat going from the surroundings to the system. That is an endothermic reaction. Okay, I want to take just a minute to kind of go through a couple of things with regard to exothermic and endothermic. These are the kind of things that you're going to need to know to do well on the test. And the troublesome thing is that with this type of concept, the things are opposite each other. And what that means is if you mix them up, it can completely mess you up. So we're going to look at the properties of exothermic versus endothermic real quick before we go through this practice test. Okay. So first of all, in an exothermic reaction, let's draw our exothermic enthalpy diagram. Okay, remember we have energy here on the y-axis, and on the x-axis we have time or reaction progress. Somewhere at the beginning on the left of our graph, we have reactants. For an exothermic reaction, the products, okay, and let's write this, products have lower energy than reactants. Okay, so that means our graph is going to look something like this. Okay, now remember the activation energy, E sub A, is the difference between the reactants to the peak of our graph. Okay, so in an exothermic reaction, our activation energy is from the reactants to the very top of the graph. Okay, our delta H, our change in enthalpy, is the difference from the reactants to the products. So we would go from the reactants to the products. That's going to be our delta H. Okay, since it's going down in an exothermic graph, okay, so I guess I need to slide this up a little bit. So products have lower energy than reactants. Since this reactants to products is going down, a second point is delta H, the number, is negative. We said from our picture, heat is going from the system to the surroundings. All right. If we would write this in a chemical equation, heat is on the right, or the product side. Okay, so if we, one other thing, if you're in the lab, when we did the Ziploc baggie lab, heat, when heat is exiting the system, your reaction vessel is going to feel hot to the touch or warm. Okay, and I want to just kind of re-emphasize where it says delta H is negative. If we would see that in an equation form, we would see something like, and then so our equation, and then we would see delta H is negative 488 kilojoules. Okay, so when we see delta H written out, it's a negative number. Okay, if we see it written into our equation, for example, if I have CH4 plus O2 produces, oops, I better slide that up, CO2 plus H2O plus, remember it's plus, even though it's exothermic, when we put it in the equation, it's plus 488 kilojoules. Okay, so that kind of goes over exothermic. So let's, and you know what, I am going to add another piece of paper over here so that I can have room to write. All right, because everything that we've just said about exothermic is essentially the opposite when we're talking about an endothermic reaction. Okay. I guess one more thing down here on our exothermic, we didn't really say it, but heat is released. Okay. Now, endothermic. If I draw my graph for an endothermic reaction, the labels of the axes are the same. This is time. This is energy. We always start with our reactants. In the case of an endothermic reaction, all right, the products have higher energy than the reactants. So our graph is going to look like this. Okay. Activation energy is still the difference. Okay. It's from the reactants to the peak of the graph. So we have to start here at the energy level of the reactants, and we would go all the way up to the peak of the graph. And that is our activation energy. All right. Delta H, same thing. It's still reactants to products. So it would be reactant, the energy level of the reactants up to the energy level of the products. And since that is going up, it's increasing, delta H is positive. Okay. What else? Heat, in an equation, heat would be on the left side or the reactant side of the equation. So if we were to see this, we might see something like and heat would be on the left. So heat would be over here on the left side of my reaction. Okay. Delta H, we said delta H is positive, so I'm gonna rewrite this equation. So if I were to write CO2 plus H2O produces, all right, heat is positive. So delta H, so we would say delta H is equal to 88 kilojoules, and it's going to be a positive 88 kilojoules. All right. Heat is going, let's say that heat is going from the surroundings to the system, which means heat is being absorbed. This type of reaction would feel cool to the touch. And that makes sense because if you're touching it with your fingers feel it being cold. The heat is going from your fingers into the container. I think that is everything. So I'm gonna put these up here for a minute and pause. And if you want to, you can take a screenshot of that so you have all of your details in one place. All right. So there is exothermic, and here is endothermic. Okay, so let's go back to the practice test. All right. Which picture is an example of an endothermic process? That would be B, because heat's entering. Which picture would feel warm to the touch? That would be A, because heat is coming out. Which picture would have a negative delta H value? Okay, negative would be exothermic because heat is being removed from the system. So that's going to be A. All right, for the delta H for a reaction is 300 kilojoules per mole. And notice that this is positive 300 kilojoules per mole. Determine if each of the following statements is true or false. Okay, so think about this. If it's got a positive delta H, that means it's endothermic. Okay, so now we need to answer these questions thinking that in mind. Heat is moving from the system to the surroundings. That would be false. Heat is moving from the surroundings to the system. And we look at our picture up here, that's what's happening. So that's going to be true. The process is endothermic. True. The process is exothermic. False. The energy of the products is lower than the energy of the reactants. Now, when I think about this, I actually think about the picture. So I draw my picture. So the energy of the products is lower than the energy of the reactants. Products, reactants. So that's false because the energy of that's an exothermic graph. Okay? If we had the graph where the reactants are at lower energy than the products, that would be an endothermic graph. Which of the graphs below is endothermic? A is endothermic because the products are above the reactants in energy. All right, identify each of the following as endothermic or exothermic. Here's where your little sheet of notes would be helpful. So exothermic is B. So this graph we've said is exothermic. Here I have energy on the left of my equation. That's going to be endothermic. Here I have energy on the right side of my equation. So that's going to be exothermic. Energy is absorbed. That's going to be endothermic. So we have H2 plus F2 reacts to give us 2HF and heat. So heat is on the product side, so that's exothermic. Delta H, okay, we've got this equation, and delta H is 5.3 kilocalories. So that's a positive delta H. That means that would be endothermic. All right. The energy of the reactants is greater than the energy of the products. So the energy of the reactants is greater than the energy of the products. That's going to be exothermic. Energy is released, exothermic. The reaction vessel feels cold to the touch, endothermic. Reactants produce products plus heat, so heat's on the right side. That makes that exothermic. Energy of the products is greater than the energy of the reactants. So that would look like this. So that's going to be endothermic. All right. Here's a enthalpy diagram. Hey, just a tip on the test when you're looking at this and it asks you to draw a diagram and it asks you to label the axes. I guarantee that there's going to be an enthalpy diagram somewhere on the test. Go and look at it if you can't remember. We've given you that information. Okay. So we want to identify. So I'm gonna label this thing. So this is my reactants. This is my products. Reactants to the peak, that is my activation energy. And reactants to products is my delta H. Okay, so the products are C. The reactants are A. Activation energy is B. And delta H is D. All right. This graph shows, this is an endothermic graph. Okay. Oh, this one has two answers. It's endothermic because energy is being absorbed. So B or D are correct. Okay. So let's go on. According to the diagram to the left, what is the activation energy of the reactant? Okay, remember the activation energy is the difference between the reactants and the top of the graph, so the difference between 500 and 800. It's increasing from reactants to the peak, so that's going to be a positive 300 kilojoules. Okay. According to the diagram above, what is the change in enthalpy for the reaction? So remember, enthalpy, delta H, is the difference between reactants and products. So that would be the difference between 500 and 100. So it's going to be 400. Remember, it's going down. So that's going to be negative. So that is going to be D. Okay, this is one that a lot of people miss and it leads to confusion on the next three questions. Okay, when bonds are formed, okay, energy is released because the bonds are making the compound more stable. So it releases that extra energy. When bonds are broken, energy has to be absorbed. Okay, so when energy is released, when bonds are formed, and absorbed when bonds are broken. So that is going to be B. Okay, now these next three questions really tripped people up. What we're doing is we're just giving you, instead of having you look at the table with all of the bonds in it, we're saying an oxygen double bond takes 495 kilojoules per mole, okay, to break it or to make it. So the question then is, what is the delta H value when the bonds in 0.25 moles of O2 are broken? Okay, so basically this is saying this is for 1 mole. And it's asking us what it would be if we only had a half a mole. So all we have to do is we take this number, 495, multiply it by 0.25, and we get 123.75. Okay, so first of all, our answer is going to be 123.75. Now, the part that we have to decide, positive or negative, the bonds are being broken. When bonds are being broken, energy is absorbed. Okay? Okay, when energy is absorbed, delta H is positive because that's an endothermic process. So that's going to be plus 123.75. Okay, energy has to be absorbed to break bonds. Okay, here's another question, the same thing. We've got the O double bond O, 495 kilojoules. What is the delta H value when the bonds in 2 moles of O2 are formed? Okay, so first of all, 2 moles, if 495 is 1 mole, what's 2 moles? 990. Okay, so we can eliminate these two because we know our answer is going to be 990. The question is that positive or negative? Well, this is telling us that the bonds are formed. So when bonds are formed, energy is released, which means delta H is negative. So this is going to be a negative 990 kilojoules. All right. And then finally, if the bond enthalpy of this carbon oxygen double bond is 799 kilojoules per mole, how much energy would be absorbed to break the bonds in 2 molecules? Okay, so we could read this as 799 kilojoules per mole or kilojoules per molecule. So it's saying here we have 2 carbon dioxide, two CO2s. Within this, we have 1, 2, 3, 4. So we have 4 carbon oxygen double bonds. Okay. If each of those is 799 kilojoules, we're going to do 4 times 799 is 3,196. Oh, check it out. This one's nice because it gave us a bunch of different answers, but they're all positive. Okay, which makes sense. The energy is being absorbed. So that's going to be 3,196 kilojoules. All right. Okay, now the back. So the beginning, I think is easier, but then I think we just haven't done the bottom part. So we're going to talk ourselves through this. So here we have a carbon oxygen triple bond. So that's 1,072 kilojoules per mole. Then we have hydrogen bond. We have 2 of them. So hydrogen is 436. So 2 times 436. Oops. 872. So we add 872 and 1072, and we get 1944. Okay. Now, on the product side, we only have 1 product. We got to count the bonds. So we have 1, 2, 3 CH bonds. We have 1 carbon-oxygen bond and 1 oxygen-hydrogen bond. Okay, so let's see. Carbon-hydrogen is 413. Carbon-oxygen is 358. And oxygen-hydrogen is 463. Okay, so let's figure this out. So we've got 3 times 413 is 12.9. All right, and then we're going to add that plus 358 plus 463. So the total here is 2,060 kilojoules. Okay, now to figure out the delta H is the bonds broken minus formed. So broken is 1944, and we're going to subtract 2,060. And what do we get? We get 1944 minus 2,000. Whoops. Oh my gosh, I can't plug things into the calculator this morning, guys. Minus 116 kilojoules. Okay, now this question, so many people miss this because we just haven't done it a lot, but let's look at this. A thermochemical equation is just the chemical equation incorporating the energy. So if I were to rewrite this, first of all, I've got a negative energy, so that means that this is an exothermic reaction, and energy is going to go on the product side. So I'm going to rewrite this CO plus 2H2. So what I'm doing, I'm just rewriting this and I'm going to put my energy on the right side. Now, big thing. First of all, because it's negative, it goes on the right side of the arrow. But when we put it in, we put it in as a plus because our chemical reaction is just telling us what's being produced. Okay, so this would be your thermochemical equation. All right, now when we draw the graph for this, I'm going to put time, energy on my axes. Okay, so I've got that. Reactants and products. So I got to think about this. This is an exothermic. Now, I don't need you to worry about the numbers from the math. I'm really just concerned about the shape. Okay, so what I'm really looking for is reactants, products. I'm asking you to draw me an exothermic graph because the reaction's exothermic. Okay, so I've labeled reactants and products. Activation energy. Remember, activation energy is going to be from reactants to the peak, and change in enthalpy is going to be from the reactants to the products. Okay, so that's what your graph should look like. All right, and then down here, this kind of trips some people up too. This is just asking you to use this equation to calculate kilojoules. Okay, so if 88.5 grams of carbon monoxide, which is CO, were reacted, how many kilojoules of energy would be produced? So the first thing we have to do is we've got to convert this to moles. So 1 mole of CO, carbon is 12.01, oxygen is 16, so we get 28.01 grams as our molar mass. And then we're going to use our balanced chemical equation. So 1 mole of CO is 116 kilojoules. And remember, that's negative. So if I plug this into my calculator, I get 88.5 divided by 28.01 times negative 116. My answer is negative 366.51 kilojoules. Okay, so hopefully that was a little bit helpful. I think if you look at this video, you will see everything that you will see on the unit test for thermochemistry. Have a great day or evening, whatever you are doing, and I will see you in class. Take care.